So we've looked at function composition as a way to double check our algebra and make sure we've actually found a genuine inverse. We can do the same thing by graphing. We'll start simple, just looking at a relation, a collection of three ordered pairs. If I want to find the inverse of that relation, I just need to switch the x and the y values. So -1, 6, we'll have a 0.6, -1. Note, just flip-flopping the x's and the y's. I can do that for all 3 points. So now I have a relation in blue and its inverse in red. Let's graph those together and see if we notice anything. So here we have the blue points representing the original function and the red points representing the inverse. So if we look at these two sets of points, one thing that may stick out to some of you is that there's actually a reflection happening here. If we look at those blue points, there's a reflection over that 45-degree line to get those points on the inverse. That line is y equals x. It's a line with a slope of 1 and a y-intercept of 0. That's our identity function. When we compose f and f inverse, x is what we got back. So this is a visual representation of that. We have our two functions, and they are reflected over that line y equals x. So we can do this with more than just collections of points. Let's look at a linear example, a straight line here. So if I have a function, I'll go ahead and continue letting my functions be blue. I've got this function, f of x, or you can think of it as y if you like, equals 2x plus 8. Well, that's a line, it has a slope of 2 and a y-intercept of 8. Let's find its inverse. First thing we want to do is switch the x and the y. That should be a y. And then we want to get y by itself. That is our goal. So in order to do that, we can subtract off an 8, which will leave me with x minus 8. Those are not like terms, so we cannot combine them, equals 2y. One last step to get y by itself, divide by 2. Be careful when dividing by 2, you're dividing that entire left side of the equation by 2. So you'll be dividing the x by 2, that's just a 1/2 x. And also that -8 by 2, which becomes a -4. So we now have what we think is an inverse. We have y equals 1/2 x minus 4. We can go ahead and rewrite that in inverse notation if we like. But instead of composing these two functions to see if we did this correctly, we could just graph them. So let's take a look at the first one here. Our original function there, boxed in blue. Well, it's linear, it's a straight line. It has a y-intercept at 8, and the slope is 2. So we'd go up 2 and to the right 1 to get a point. We could also go down 2 and to the left 1 and get a point. Let's go ahead and graph a few more. While you only need 2 lines in order, 2 points in order to determine a line, the more you have, the more accurate your graph can be. Connecting those dots will give you a nice straight line. Now let's graph the inverse. The inverse has a y-intercept of -4 and a slope of 1/2. In other words, up 1 and over 2, or you can go down 1 and to the left 2. Just like with the first line, let's go ahead and plot a few more points. And now that we have our points, we can connect the dots. So note that we have 2 lines. The blue one is our original and the red one is our inverse. And once again, we can double check that they're inverses by looking for that reflection. If they are inverses, they should be reflected over the line y equals x. Well, there's a line y equals x. And we can see every point has been reflected over that line. We even have a point where all 3 meet. How fun is that? Let's take a look at one more linear example, and then we'll move on to a parabola. So this linear example has a fraction in it, no big deal. We're still just flip-flopping the x's and the y's. So we have that x is 1/3 y minus 1, and our goal is still to get that y by itself. So the opposite of minus 1 is plus 1. Once again, these are not like terms, the x and the 1, so they just become x plus 1. A couple of ways you can get rid of that 1/3. Probably the quickest is just to multiply both sides of this equation by 3. Multiplying both sides by 3, well, 1/3 times 3, those cancel. On the left, there's a bit of a distributive property, and that'll leave us with 3x plus 3 equals y. If we wanted to write that in function notation, it would be f inverse, because this is an inverse function, or at least that's what I'm claiming. F inverse equals 3x plus 3. So we can graph these again, just to double check that we did this all correctly. Let's start with the original in blue. It has a y-intercept at -1 and a slope of 1/3. So once again, we can go ahead and put those extra points in. And once you have points, you can connect the dots. Let's also go ahead and graph our supposed inverse. It has a y-intercept at 3 and a slope of 3. So you can think about that 3 as 3 over 1, up 3, and to the right 1, or down 3 and to the left 1. Once again, we can plot a few extra points and connect the dots. So again, I'm making the claim that these are inverses. To double check that, we could just check that reflection. So let's go ahead and graph a dashed purple line to represent y equals x. And there we have it. Once again, we can see that every point on our original line has been reflected over that line y equals x. I'll do some down here too. And once again, there's a point they all share. Note that this is not needed. It is possible to have some lines that do not intersect and are still inverses. I'll go ahead and throw an extra example in here really quickly just to show that off. For example, you could have a line through those 2 points. So that line would be x plus 1. And then I could also have a line through these 2 points, which is x minus 1. Those lines will never touch. They are parallel, but they do reflect over that line y equals x. You get this nice highway-looking thing right here. These are inverses, even though they never intersect, and they don't intersect that line y equals x. So it's not completely necessary to have that intersection. It's just happened with these 2 examples, and it happens to look very pretty. So we'll go ahead and cut this video short. Yes, 9 minutes. Short, right? We'll put that quadratic example in its own video.